All right. So this is the slide of the activity we had yesterday, the discussion. Am I correct?
Yes.
Yeah, we started from here, and yeah, we went through these slides, looking at the measurement tools and technologies, sampling strategies, environmental monitoring. We went through the learning objective.
Yeah.
Please mute your mics, everybody. Please mute your mic. Yeah, we're just doing a recap. So this is something we did yesterday. We're just doing a recap. So just for us to follow through. Then we had our learning outcomes where we expressed our projected outcomes from this interaction, the whole interaction, which will end by Friday. And we also had, we looked at why we monitor the key drivers for monitoring, because this is our environment, this is where we live in. Thereby looking at the core environmental parameters, we looked at traditional versus the emerging tools in monitoring, and we looked at the measurement tools that are evolutionary, comparing traditional to emerging innovations. We looked at air monitoring technologies. Our next today's class will be moving in from here. So we looked at the water monitoring technologies. We also had a glimpse at the soil and biodiversity monitoring. And we looked at the satellite-based monitoring. And we looked at the sensor networks and telemetry. Then we looked at, after we have gathered our materials, we collected data, what do we do with it? We consider statistical sampling fundamentals, the random, stratified, systematic, and cluster approaches to statistical evaluations. And we delved a little bit into the design, the sampling designs, where we looked at the temporal sampling designs. And we also considered the quality assurance and quality control that are put in place during sampling. And we looked at the existing regulatory frameworks. And then we took some case studies like the pharma industry, environmental monitoring, looked at the case study, what happens in certain cases. And we considered future trends, carbon and methane issues, then water innovation, automations, and the influx of AI-enabled systems. And all right. And we consider the challenges that are lying ahead of us, where we looked at the technical, the data management, social, political, and equity challenges that evolved. And we concluded by, an overall bird's eye view of the whole system. We showed our references and we thanked ourselves and exited. I believe that is what we did yesterday. Is that it?
Yes, it is, sir.
Okay. Are there things that we need to talk about there briefly, just for 3 minutes before we move on? Nanev, do you have anything to say?
Hello, sir.
Yeah.
Not for now, sir.
Not for now, okay.
My concern is that of some of these abbreviations and notations, like the PFAS, the PM2, some of us are in diverse fields, and we cannot actually comprehend what they stand for.
Okay. It's all right. Okay. Subsequent classes, I think we'll start mentioning them. However, what you may do on your own, are you with me?
Yes, sir. I'm with you.
George, I hope that question is from George. Okay. George, just note down all those abbreviations that you are not conversant with. And you can either DM me directly or post it, and then I will take them up and give you a concise definitions for all of them and post it for everybody to see, because definitely you will not be the only person that has that concern.
Yes.
So
yes, sir. He's not
yeah,
the
let
only
there be
person.
good.
Yes,
Just
sir. Yes, sir.
just put them down and DM me on it, and I would respond with all the abbreviations that you are concerned about, so that this way we can move forward fast. Yeah. Any other concern?
Prof, good morning, sir. I just
Good
thought
morning.
to
Oh,
stop
my
by.
HOD. Thank you, sir.
Meet you specially.
Thank you, sir. I'm happy you are here. They have sent me to you before now, sir. I told them about the very good work of expanding the class size, and they were really thrilled and said I should extend their heartfelt gratitude. Thank God you are here. Ladies and gentlemen, our indefatigable HOD is on this platform right now with us. So we can tell him the thank you and the appreciation we said earlier on.
Thank you. We are clapping
Thank
for our
you,
HOD
sir.
and saying you're welcome, sir.
Thank you, sir.
Thank you.
Thank you, everyone,
Thank you,
and
sir.
thank you
Thank you
for
so much,
your
sir.
cooperation so far. Thank you so much, Professor.
Thank you, sir. Welcome.
I am sorry for interrupting your class. I just wanted to be sure that everything is fine. But from what I can see, I think the class is well coordinated. Thank you, Prof.
Thank you, sir.
Yes, sir. We are okay. Thank you so much, sir.
All right. Bye-bye, everyone.
Bye, sir. Thank you.
Bye,
sir.
Thank you.
Bye.
So, ladies and gentlemen, since we have no other concern with what we did yesterday, we have to move on to the next slide, which is part of what we have today. And like I mentioned before, we are going to jump in from the air quality analysis. And permit me just a few seconds to share my slide on that, and we will take it from there. This morning, we are going to look at the analysis of air samples. Particularly for... Please, can you mute your mics? Gentlemen, mute your mics, please.
Hello. Nobody sent that. Okay. That's the assistant class rep. That's the assistant class rep. Yes.
Hello, our lecturer, please unmute yourself so that you'll be the only one to speak. Unmute yourself, sir, please. Sorry, I had to.
No. It's a good one. Angu, thank you very much. I think I can be heard now.
Good. Yes, sir. So we can hear you now, sir.
I want to
we
confirm,
can hear you now, sir.
Is my slide showing? Are you seeing my slide?
Yes, your slide is showing, sir.
Okay, beautiful. So let's go ahead. We are looking at the analysis of samples. Particularly of concern are the inorganic and organic pollutants, as they are found in the environment. So carrying out an environmental monitoring of these materials is one of the very important things that one needs to look into. And for us to do this, we have some objectives in mind. One of which is that at the end of this interaction, you should be able to identify major inorganic and organic pollutants that are of concern to humans and the environment, because it's not just about humans. The animals are also affected, the insects are affected, every living organism within the biosphere, they are all affected in one way or the other. So we should be able to bring you up to the speed of identifying major inorganic and organic pollutants that are of concern. We also have this objective of making you be able to explain the fundamental principles of active and passive air sampling techniques. There are two major ones. There are ones that are for active and there are ones that are passive. Passive in the sense that they may not be a direct impacted sampling process, but they are also part of sampling. Then we should also be able to get you to describe common analytical methods for key inorganic and organic pollutants. The other one is to also ensure that you are able to discuss, the importance of quality assurance and quality control. You can see the abbreviations like somebody mentioned QA and QC, though I mentioned it the other time, in air analysis. And then you should be able to recognize the challenges and limitations associated with air pollutant analysis. In the way of introduction, I would want us to understand something about the air sampling thing. This the atmosphere as we know it is like a sink. This sink is in this form of accepting everything that comes into it. It is open to anything that comes. So the air is just the primary exposure pathway for humans, for the ecosystem. And what is it exposed to? It accepts everything. It accepts the good ones. It accepts the bad ones. The bad ones we call the pollutants. The good ones we call those that nourishes our lives in one way or the other, such as the oxygen that we use. While the bad ones for us human beings are the CO2s, for example. I'm just giving an example. And we should also understand that it is very, very important that we know some of these pollutants as they are. Air sampling analysis, particularly in the environmental monitoring process, is targeted at detecting these pollutants, whether they are organic or inorganic. And this detection, as per monitoring, helps us to, first of all, state the quality of the air around us, and at the same time, identify the sources of these pollutants, and of course, ensure the regulatory compliance or standard methods, that are involved. I would shortly mention these pollutants and then we'll move on. Some of them, like the inorganic ones, are things like the carbon monoxide, that's CO. We'll have the carbon dioxide that I mentioned before. We have the NOx that we mentioned like yesterday. We have the SO2, sulfur dioxide. We have the O3, which is the ozone. And we have the NH3, which is the amides, the ammonia and their group. And we have the HUS, hydrogen sulfide. Let me relate hydrogen sulfide for those of us that are not very deeply science-based. Sulfide is that gas that smells like rotten egg. When you have an egg that is spoiled, that's very awful smell that you get. That is how HUS smells. And some of them come from combustion of industrial practices. So you find out that one, they impact us. One, during our health metabolic processes, such as respiratory processes, cardiovascular arrangement, carcinogenic effects. These are things that they bring to impact on our health. You know of when you are told to inhale, not to inhale certain things, like I mentioned the other time, the nanoparticles and the microplastics, nanoplastics and microplastics. Some of these things accumulate and they trigger certain carcinogenic effects. They also impact the ecosystem and cause damages. And how do they come in? They come in as in the form of acid rains, eutrophications. They also damage ozone layer. And of course, because of the GHGs, that is greenhouse gases, they cause climatic changes, which have very detrimental impact, and very readily known, they cause material degradation. These are some of the impacts that we know that occurs with these pollutants. It's not about the particular pollutant now, it's about the general cocktail of these pollutants. But in all its this thing that we know, the as said now, are classed under two categories majorly: the inorganic, which I have mentioned, and the organic. And the organic pollutants are, some of them are like the volatile organic compounds, which we call VOCs, VOCs. And then we also have the semi-volatile ones like the PAS. We have the pesticide, we have the PCBs, and these are then the PFAS, which we'll get to know later. We also have the polyurethane foam that we use. You discover that polyurethane in its very chemical active state is not a very good material for contact, to come in contact with. However, when it is formed as foams and are trapped, we can use them for a while. We have various other ones, but we would to know them as time goes on. Then, like mentioned yesterday, we have regulatory drivers, which are instituted authorities that carry out oversight function of what we have in the environment, how we handle them, and there are procedural means of identifying their presence and quality. Presence, quality, and quantity, as the case may be. So some of these regulatory drivers are compliance, that is compliance with National Ambient Air Quality Standards, National Ambient Air Quality Standard, NAQS. We also have the EU Air Quality Directives, and we have the WHO guidelines, which also interrelates with the workplace exposure limits, or what we call them, the OSHA PELs and the ACGIH TLVs. Then, in all of that, we have our environmental monitoring goals, which happens to be having our baseline assessment. We look at the trend analysis. We also look at source identification and appointment. We consider compliance verification, and we have our exposure assessment. Then we have our research. These are environmental processes that guides our moving forward. Now, we, like I mentioned before, we have our inorganic pollutants, which we have categorized under the gases, the particulate matter, that is solids, the metals, the acid species, the cations. For the gases, we have, as mentioned before, the sulfur dioxide, the nitrogen oxides, that's nitrogen, NO2, and NOx. The X there represents any sub-valent of the oxygen material. It depends on the oxidation state of the oxygen that is attached to the nitrogen. And that determines also the level of toxicity of that particular nitrous oxide. Then we have the ozone, like I told you, the O3, then carbon monoxide and hydrogen sulfide. Then, of course, the ammonia. These have been mentioned before. These are classes of inorganic pollutants that come as gases. While we have the particulate matter, that is the solid, tiny fragments that are designated as capital P, capital M, subscript 2.5 and 10. These materials are most likely contaminated with metals and ions, as the case may be. So because of that, they are considered pollutants, because apart from their physical states of being solid and not easily digested when they are ingested into the or inhaled into the body, the metal content, the metal component of their entity also plays a very dangerous role in our overall well-being. Then the other, here we class some of them based on the standards, the two standards that we have, the upper limit of 2.5 and upper limit of 10, as the case may be. Then we have these other inorganic pollutants in the nature of metals, lead, arsenic, mercury, nickel, cadmium, chromium, selenium, boron, a lot of them. When once these metals come into contact with our body, to some extent, they are considered heavy metals. You will hear people talk about heavy metals, heavy metals. Heavy metals in the sense that they are not easily degraded or reduced to appreciable sizes that they can be managed by our system. They are heavy metals because their crystal lattices are big enough to cause scientific or biological interruptions or disruptions. Then we have this other group that are acidic species. That is, remember I mentioned the acid rain and other things. Here we have the sulfuric acid, H2SO4, we have nitric acid. These materials, and even the carbonic acid, because when rain falls, it dissolves some of the CO and CO2 found in the atmosphere and delivers this as acid rain. They are delivered as acid rain. Acid in the sense that their pH is towards below 5. Any pH that is from 5.5 to 1 or 2 is considered acidic. So when the rain dissolves some of these acidic species that are found in the atmosphere via rainfall, you have a lot of acidic rain that people, if one will remember, there was a time people around Port Harcourt were complaining and talking about the rain suit. Rain suit happens because the refinery there had their refining process spewing out soot into the atmosphere, and while the rain falls, the rain brings down this soot as a form of rain. The same thing happens with these acid species. So we also have the cations or anions species, where you find the sulfate, the nitrate, the ammonium species. These are all under inorganic pollutants. Now, the other one is the organic pollutants. These organic pollutants come in the form of volatile organic compounds, VOCs. And examples are the benzene, toluene, ethyl benzene, xylenes, and formaldehyde. Formaldehyde is a component part of what the people use in the production of the wood adhesive, that adhesive they use to make wood. Formaldehyde is also used in the hospitals in the form of formalin in embalmment processes. That will tell you how bad it is. I want to clear it here that formaldehyde is not formalin. Formaldehyde that is dissolved in water becomes formalin. Formalin is a liquid component or liquid type of formaldehyde. Formaldehyde as it is gaseous. Formaldehyde can also be solid. So when you say formaldehyde, you know that you're not talking about the liquid component, but when you say formalin, you are talking about the liquid component. Please let us note that. These are some of the takeaways, fresh takeaways we will have from this interaction. Now we have the chlorinated solvents such as the TCEs and PCEs. And of course, we have the polycyclic aromatic hydrocarbons, the PAHs, polycyclic aromatic hydrocarbons. There are others that are semi-volatile, that are known as SVOCs. These are heavier PAHs, polychlorinated biphenyls, that's PCBs, organochlorine pesticides, OCPs, dioxins, and furans. Then we have the phthalates and the phenols. I want to specially point us to the phthalates. The phthalates are used primarily in the plastic industries. Every rigid polymer that you have is made plastic or flexible by introduction of some of these phthalates. For example, the plastic bottles you use, any plastic bottle that is made from PET, polyethylene terephthalate, has a component phthalate ingredient because these are plasticizers, but they are not good for us. However, for now, we have very limited or no alternatives to this material. So we keep using them and keep trying to play safe by the way we use them, we handle them, and all that. Phenols are also another group of chemicals that are important in the industrial processes, but have adverse effects on us. So when you talk about phenols, they have their good sides and they have their bad sides. Now we have the persistent organic pollutants, POPs, and these are called persistent because they don't easily go away. Their shelf life is so large that they are there for a very long time. So the chances of contacting them, even after they have been used in a particular environment, is very high. So they become a threat to our existence and safety. And the safety of the environment. Now, the semi-vox fall under these categories, such as PCBs and the OCPs and PCDDFs. Now, for us to look at air sampling, there are steps that we must take. These are critical steps, and one of which is the representativeness. The sample must reflect the atmosphere being studied. That is, you remember we mentioned the GIS thing. Now we are looking at mapping. The location must be identified. The time of this sampling must be clearly stated, and the duration of this sampling must also be stated. Why do that? One, a particular location where you have sampled maybe say around 10 a.m. in the morning, and as at that time the particulate matter, incidence of particulate matter may be high, probably because the rate of car traffic along the road close by was at its peak at that point when you are sampling. Definitely you have more particulate matter being spewed into the environment. Now, give that same environment 20 minutes or 10 minutes from that time. There may be other things. One, traffic flow might reduce, which also affects the amount of spewed in particles. Or there may even be watering and damping of the environment, which also controls or brings down the volume. So you must first and foremost establish location, the time, and the duration of your sampling. So it's like a garbage in, garbage out principle. What you give is what you take out of it. I can go to the same sample site at a different time and generate different data from that particular sample. So we only compare this based on location, time, and duration. Then the other thing to consider is the sampling strategy. You need to define the objectives. What are you looking out for? What do you really want to establish? Now you find out that there are particular sites that you select for a particular reason. Excuse me.
Sorry, sir.
Yeah, the selected sites. Selected
Sorry,
sites.
boss. Maybe if you
Thank
send for water.
No
Sorry.
worries. Thank you. Thank you very much. The selected sites will align with your one of the set objectives. Let's take a typical example. For those of us who are very, conversant with metropolitan areas, if you go into, let's say, Abuja, for example, and you want to sample a place like Maitama, the parameters and objectives for sampling Maitama may not be the same for sampling a place like Gishiri or Maraba or Nyanya. Why? Because the activities around these areas, they differ, both in nature and quantity and quality. Now, go down to the outskirts of the same Abuja, you discover that water quality parameters may differ too when you are sampling. So you have to set your objective. Coming to here, the parameters and objectives for sampling the environment around the bridge, the new bridge area, I mean in Makurdi here, will definitely be different. For example, around that new bridge area, there is a slaughterhouse, there is an abattoir. So compare that area to when you get to government house area, where there are no abattoirs, there are no slaughterhouses, and there is no market activities there. So one, the strategy will differ based on your defined objectives. Then you select your site. What is the background of where you are going to work? Like I've just mentioned. What is the source impact? I've also said that. And what is the population exposed to the impact? So these are the things that you must consider before starting your sampling. Then you determine the frequency and duration, of course. Now, what are you going to do? The grab, integrated, or continuous sampling approach. The grab is a kind of one-off thing. Integrated has to do with where you have a lot of other things and sampling volumes and situations all coming together and trying to form an opinion about a place. Let me clear that. You see, taking the new bridge area, when you want to pick your sample, you are looking at air quality. You are going to consider the fact that, there is also a rice mill nearby. So definitely there will be this smoke from the boiling of rice. When they say they are parboiling, they use fuel wood to cook. So there will be smoke. Now, when you go to the abattoir, the same location, you discover that, these guys are also using tire, that's car tire, to roast the meat. What is the composition of car tire? Car tire has in it, apart from other things, sulfur. So when you are now strategizing, you also have to include identification of presence of sulfur. Now, take this same scenario to North Bank Market. For those who know North Bank, North Bank Market, they don't have such a slaughterhouse there. But it's the same, there's an abattoir, of course, but it's not as intense as that of New Bridge. So you may not even discover or sample for sulfur. So these are some of the things that you need to know. Now, are you going to continue carrying out sampling on this location over a period of time? For example, are there periods where the incident and impact are felt more? Or is it just a periodical thing? These are some of the things that you need to consider. And you then strategize your sampling activity. Now, having said that, let us look at some of the major sampling techniques that are involved. Like mentioned before, we have the passive sampling. Then the passive sampling principally tells us that there is this diffusion and permeation of pollutants either onto or into a collecting medium. This is the principal point of consideration. Now, this principal point of consideration helps you to understand what you need to use. I'm talking about aids like the filter paper, a badge, a solvent. Like the other time I mentioned the former class, I mentioned booms when it comes to oil spills. So the principal thing is the diffusion or permeation of pollutants onto or into a collecting medium. Now, if you are sampling air, that is what we call an air analyzer, air quality analyzer. It's I wish some of you will come around the lab area and around this place. I will take you to where you see an air analyzer. It's an equipment that you just drop it around the environment where you are sampling. Now, this material collects air from the environment around it and stores it on you have a medium where it stores it. Now, at the end of the period you want to expose it to that air and its pollutant, you collect the medium and start your analysis as it is. We also have situation where one wants to study something like harmattan dust, the composition of a particular harmattan dust. You know, when harmattan comes, it comes with the airflow, and that airflow moves across different environments and settles at different places and locations. When you are studying the harmattan dust composition around a particular area, because some of these harmattan dust have been shown to have positive impact on agricultural crops. They come with a minimum amount of potassium and not the rest of them, even phosphorus carried from where we don't know. But in doing that, what you bring and expose are surfaces like the filter paper, where dust accumulate over time and you harvest and carry out your material. Now, you can also have, and remember that with the filter paper, you are depositing the pollutant onto the surface, not into. While for some solvents, if you expose some solvents, these solvents have the tendency, the potential to be able to absorb, not add, absorb some of these pollutants into their matrices. And once this is done, you harvest them and extract the pollutants and carry out your analysis. So it depends on what you want to do. This is part of the techniques and approaches when it comes to passive sampling. And it is driven by concentration gradients. That is what concentration of it you are looking at. And you don't have, no active air pump in it. So you determine some of these things while you are considering your approaches and your experimental design. That's where these things come into serious play. Now, the advantages of these passive sampling principles and approaches are, one, you can see that they are very simple. Like the harmattan dust collection, you just place your paper and you collect. They are also inexpensive. Then you use lightweight materials, and it is a quiet thing. Just like I mentioned, You carry the equipment, drop it there, and go away. At the end of the time you have proposed to sample, you come and pick it up and collect the material where it is deposited. You don't need any power. What I mean by power is you don't need electrical power to power any of these things. So power consumption is almost zero or near zero, as the case may be. And it is good for special mapping. You know, you do it within an environment, and of course, you easily do your GIS mapping or your AI automated or empowered location systems. Now, you can also, with this passive sampling, carry out long-term integrated samples. You know, I showed, for example, the Hamatan dust collection. You can place that over a period of 1 month, 2 months, or the period all through which the Hamatan season is there. And at the end, when the Hamatan is receding, you can go and collect it and then collect all the things you want to collect. So it can use it for long-term integrated sampling approach. But it has disadvantages of its sensitivity is lower and it's not very active. The flow rate, it's dependent on experimental factors. Yeah, wind, speed, the temperature, the humidity. Example of humidity playing a part there is, assuming one of the days where there is Hamatan, you know, there are times when you come out during the Hamatan period, you experience a kind of dew. Now, when this dew falls on a particular day within this period, it dampens the surface or the collector material and may probably wash off any material that may be contained in the dust that have been accumulated, giving rise to non-identification of this particular item. So these are some of the disadvantages. And of course, like we said, it requires longer deployment period because we need to expose them for a long time to be able to detect levels of this, because they need to accumulate. They need to be big enough to be detected. So it requires longer deployment for detectable levels. So it is not good for a rapid on-the-spot assessment. So we don't have to deploy that where, you know, for example, where we talked about yesterday, where we use sensors, you know, to approach these things. No. Now, you also require calibration. And calibration at this moment should be done based on the moment conditions. So calibrations will differ from one point to the other or one duration to the other. So it becomes a complex thing when you have different calibrations, different conditions, and you're analyzing something over a period of, say, 6 months, and you have a lot of calibration standards. It becomes a problem. And on the slide there, we have seen that we have different examples of some of these things. And I don't want to get into that because of time, but we can discuss it later on our own. Then the other one is the active sampling approach. The active sampling approach is based on the principle that where air is drawn actively through a collection device using a calibrated pump at a known flow rate for a specific time. Now we are looking at the use of equipment, a powered equipment. Remember, the other one, the passive, there was no power involved. Now we are using an equipment that has to be powered, has to be deployed over a time. And what does it do? It takes air in from the environment where it is, and it has to be at a particular period, duration, and location. Remember, these three are always there. We have to talk about the location, we have to talk about the time, you have to talk about the duration you are deploying this. So this provides a time-weighted average, and of course, which affects concentration. It is concentration per time per period of deployment. Like I mentioned before, you may deploy it at, say, specifically 10:30 a.m., when there is this heavy flow of traffic, and you allow it for a period of 1 hour, that means by 11:30 a.m., you are standing it down. If somebody, and this is within the peak hour of traffic in the morning for a cosmopolitan area. Now, if you go back to deploy this same machine, the same location, for the same time of 1 hour, around, say, 7 p.m. or 12 p.m., you will never get the same thing. You may likely not get the same thing because of flow of traffic. So that is why it is a time-weighted average concentration. So these are things you have to put into consideration when considering these facts. Now, what are the components of this equipment that we're going to deploy? It has an inlet, and it has a collection medium. It has a pump, has a flow rate, flow measurement and control. Like I mentioned, if any of you have the time, when you come on the school, particularly the College of Social Sciences, I can take you to a place where you will see one or two of these equipment we are talking about. Now, apart from the inlet, the collection medium, we have the media. Now, media is where these materials, the pollutants, when they are accepted in, they come in and they are deposited there. That is where they are received. And we have different media that we have talked about. We have different medium. We have the filters. We use the filters for particulate matter and particle-bound pollutants. We have them on, as you see them on the slide there, the hydrogen peroxide, that is H2O2, for the absorption of SO2. We also have this, the H2O2 there serves as the subfilter onto which the SO2 is set to attract the NO2s, and then they have the TCM to attract the mercury materials. Now, we have the quartz fiber. This quartz fiber is also deployed for organics and ions. Teflon is used, though Teflon is inert, so it is used for metal ions, and while glass fiber is less commonly used for also metal ions. Cellulose, the cellulose we know, is also used as a filter material deployed with this equipment. And we have the sorbent tubes. These are for the gases and the VOX, and they are packed with materials like the activated coal. The activated charcoal serves now, depending on the means by which it was activated. You can activate the charcoal using an acid. You can activate a charcoal using heat. It depends on the means of activation, though. So the activated charcoal can serve as a non-polar for a solvent for non-polar VOX, while silica gel serves for polar compounds. Tenax, which is a proprietary item, serves for VOX and then thermal desorptions too. And of course, we have the XAD resins, and these are proprietary materials and molecular sieves. And we have another component known as the impeller or bubblers. Here, air is drawn in through a liquid absorbing solution. Most times, we draw them in, and then we trap the air there, and we analyze the air from there. There are situations where, from an impeller or bubbler, you can directly feed one of the analytical equipment like the GCMS and LCMS equipment. So that serves as one of the collection or media for collection of some of these pollutants. Now, the advantages of this active sampling is one, it has the advantages are one, it has this higher sensitivity, like mentioned before. It gives you real-time analysis of some of these things. It's faster in a sampling of target levels, and it's better defined. It has a better defined sampling volume and rate. Of course, it has this very wide application method that you can use, like I mentioned, using the integer collecting and then directly transferring to the equipment, which cannot happen with the other passive sampling approach. Now, the other advantage of the active sampling is that it is suitable for short-term compliance sampling. Yes, I said so, that in field activities, field research, or on-the-spot assessment, probably there is an incident and a quick on-the-spot assessment is desired, that the active sampling approach or technique is most suitable. For that, it gives you deploy immediately, collect your results, collect your data, bring out your results, and advise accordingly. But it has the disadvantages of requiring power, because the pump is powered and of course becomes more expensive in operation. Apart from the fact that the equipment itself is expensive, and you also experience a kind of pollution in the form of noise pollution, the use of the equipment, because it requires pump and the pump hums, and of course you need to calibrate and maintain this equipment. So that makes it a little bit complex, and it's an disadvantage to its approach. And of course, having looked at this, we have particular techniques that we use for both inorganic and organic pollutants. For the analytical techniques for inorganic pollutants, we have the gases, we have the particulate matter, and we also have the metals, ionic species, as the case may be. Yeah, and when we look at some of them, we discover that for gases such as the SO2, NOx, O3, and CO, there should be an established reference methods that must be abided with. Some of these reference methods are based on photometry, and after collection in a solution, we subject them to this analysis. Some of the analyzers that we use are the UV fluorescence, where we particularly use for the detection of SO2. And then look at the chemoluminescence approach for the NOx. Here, it is based on a reaction with O3. As the name implies, it's the luminescence that is observed when there is a chemical interaction between these species. You have a particular detection luminescence, and is based on the chemical interaction. Then we have the UV photometry. UV photometry is deployed for ozone detection, while the non-dispersive infrared is both suited for carbon oxide. Now, for particulate matter, we deploy, for example, after we've collected the deposited particles from the the other filter paper exposed to the environment. We collate, we harvest the particulate matter, and we use gravimetric analysis for their detection, particularly the quantity, as the case may be, because you would be able to identify and say, oh, within this period of time, so milligrams or grams of harmattan dust was deposited around this environment. So there we use gravimetric analysis, which is about weight. Now, what do we do with that? Filters are weighed, that's pre-weighed before you drop them. Then after collection, you weigh them and then do the calculation that will give you the actual weight of deposited particulate matter. Now, we also need to carry out, because there are two basic sizes, particulate sizes, standards, which are the 2.5 and the 10 mm and 10 size, particulate size. We also have to use another method, which is not gravimetry per se. It's more or less on size distribution. The DLS is the machine that we use for that, and that is a more advanced analysis when you want to go further to say, okay, within these collected samples, that so quantity or ratio or percentage of it falls within 2.5, while this other one falls within 10, as the case may be. So for the inorganic pollutants, we are still looking at the sampling for acid digestion is carried out, because when you are able to digest, you'll be able to exclude the unwanted or the material that we are not interested in. So what do? We carry out acid digestion. And in carry out acid digestion, we have different kinds of digesting fluids, one of which you must have heard about. This is aqua regia. Aqua regia is a combination of HCl and HNO3 in the ratio of 1:3. And you have the hydrogen fluoride media. You have, it depends on what you want to do, what your target species for identification is. There are species that are very stubborn and that you need to use harsher, so to say, solvents to digest them. So now we will have different approaches to that. You can do your digestion using the simple heating, or you can use the microwave assisted process. You can also use the maceration process, the cold maceration approach. It depends on what your species of interest really is. Now, the other analytical technique that are employed, which is now the main analytical approach, because all this while we've been dealing with sample preparation, is the use of inductively coupled plasma optical emission spectrometry, ICP-OES. I would want you to, on your own, take a look at this ICP-OES. A amount of time, we can't pick them one after the other, but I'll try to explain some of them as we go along. No, now, this equipment simultaneously determines elements, many elements at the same time. And you don't need to do one element at the time. That's what it means. You just put in your raw sample, your crude sample, and ICP-OES analyzes the crude sample and brings out all the information that is related to every element that is present in that crude sample. However, it is moderately sensitive, but at least it gives an idea of what is contained in your crude sample. The other equipment is the one that is known as the inductively coupled plasma mass spectrometry, ICP-MS. Inductively coupled plasma mass spectrometry. Its sensitivity is very high and has a wide dynamic range, and is used in identification of isotope, and it has this gold standard for trace metals. It is at the top there when it comes to analytical equipment for detecting the particulate matters as it is. Then we have the AAS, which almost everybody, I believe, in this class knows. AAS is simply the atomic absorption spectroscopy. It is used for detection of metals, what we call heavy metals like lead, cadmium, chromium, arsenic, and the others, cobalt, and the rest. Then we also have the thing is the gas that is used to burn them comes from an oxyacetylene oxygen combination, and the heat is capable of causing the metals contained in your sample that is aspirated. Though the metal in your sample that is aspirated, it causes them to ionize and give off a particular luminescence, which is detected by the readout equipment component. That way you can identify the metal present. The other one is the flame AAS, which is also less sensitive but works on the principle of flame, individual flame characteristics and identification for metals like sodium, potassium, particularly the group 1 metals, Then we also have these AAS have degrees of sensitivity and sophistication. Some of them have what we call the graphite furnace. The graphite furnace allows for high temperature operations, So we have the GFAS, which is also high in sensitivity, particularly for single elements. However, because of its high costs due to its sophistication, it is less commonly used now compared to the ICP. ICP is cheaper and faster and gives you same result, if not better results. So the GFAS is, as it is now, in less use, not demand per se, than the ICP. So everybody's going to ICP OES because it's cheaper when it comes to function, use, deployment, and it's as good, if not better, than the GFAAS. We also have another version of the AAS, which is called the cold vapor atomic absorption and fluorescence, CVAA/CVAF. This is meant specifically for mercury. No, mercury is a special metal. That is the only person that answers the liquid metal, because we know metals to be solid, but mercury is liquid and it has its peculiar characteristic properties. Now, for the ionic species like SO4 2-, SO3-, NH4+, that are deposited on filters. We prepare them by first extraction with deionized water. That is, when they have been trapped or when they have been collected, we extract with deionized water. Deionized becomes very important because these are ionic species. They are ionized. So you don't need to use a solvent that is ionic to extract it. There will be interaction. So use a solvent that has been deionized and doesn't have any ionizable potentials to extract it. And you do that using the ultrasonic bath. And we use ion chromatography, IC, as a analytical technique in its detection. The primary method as we have here is that it separates ions based on affinity to ion exchange column. So that way, in ion exchange column, there is a tendency for the ionized material to be trapped or released as it flows through the ion exchange column and is detected by conductivity, how much of it comes in. For example, you have, when there is a positive and negative charge, there is a current flow. This current flow is what is used in the detection of the ionic species, as the case may be. And of course, simultaneous analysis of these cations or anions are carried out, because if on the ion exchange platform you have a positive coming in, where it will align with the negative part of the ion exchange material and generate current that can be detected. And when this is done, it is transmitted to a readout. This readout gives you an idea of, oh, there are maybe this particular current flow is a result of this item, this material, or this voltage. It depends on how you want to run through it. So, having said that, we are now going to look at the organic pollutants, because all this while we've been talking about the inorganic pollutants and what do we do with them? There are things we must do to get good results, valid results, verifiable results, reproducible results, so that if someone follows our description of our activity, the person can reproduce the same results. Now, one of them is, for under sample preparation, is solvent extraction. For us, after we have collected all the deposited material or the pollutant material, we are supposed to look at the way by which we can extract our pollutant of interest. And that is what we need to do to prepare for the extraction. Now, we have solvent extraction using Soxhlet. We also have accelerated solvent extraction. We have ultrasonic extraction. And I want to add here that we also have the one that is assisted by the use of the what do you call it now? This equipment, the microwave. So that we call it the microwave assisted extraction. Simply using microwave to heat at a short period. There is a burst, you give a burst of heat, it blasts through the material, and as it blasts through the material, it extracts the organic pollutant of interest from the media that it was absorbed or adsorbed on or in. Now, the solvent extraction works on a principle where a material is contacted by pure solvents that have been boiled, volatilized, and condensed into the solvent extractor. Most especially, the material is put inside a timbo, and this boiled, volatilized, and condensed solvent meets the sample inside the timbo, inside the sucklet, away from the main boiling flask. So this continues over time until at least 6 hours, until the material is exhaustively extracted. Now, the accelerated solvent extraction, all of them are almost the same thing. The difference here is that the burst of energy, the blast that gives us energy to it, because it's now heat energy, it's for solvent extraction, a minimum of 6 hours is required. But for microwave assisted or the accelerated process, it takes a shorter period of time, but a much more huge amount of energy is sent through the system at a very short period of time. So that makes it possible to do the extraction within a short period of time without necessarily, exposing the material to a long duration of extraction. And it kind of preserves the integrity of the substrate and the pollutant as it is. Okay, you look at after this is done, we also have the process of thermal desorption, TD. This is where direct heat, the direct heat is applied to the sorbent material. Remember that sorbent material at this point has the pollutant of interest with it, and this direct heat sorbent, direct heating of the sorbent now excites the sorbent to release the pollutant as it is, and thereby dissolve the either VOCs or SVOCs into a carrier gas, and this is then channeled to a GC injection, or what I call the GC kitchen. Now, here the advantage with this is that you ensure by this process that you come in contact with little or no solvent. It's just a blast, a blast of heat. So this is done because it's highly sensitive and it's very sensitive for VOCs, which on their own are also sensitive. So it's an advantage. It has an advantage over the conventional solvent extraction process. Now, we also have the purge and the trap. That for VOCs in liquid samples, that is the impingers or sample extras, the inert gas purges VOCs from the liquid, traps them on a solvent, then thermally dissolves to the GC. But remember that for those of us in this divide, in this part of the globe, this may not be very easily, accessible That is why oftentimes, you discover that the solvent extraction processes or the microwave assisted processes and all that are basically deployed in some of these techniques. So the other one is the cleanup process. This is important because the complex matrix of the VOCs, and they need to be handled carefully. And such techniques as the gel permeation chromatography is mostly adopted, while solid phase extraction and acid-base washing are also deployed. But the fact is that there is this cleanup that is supposed to be done, and the materials cleaned up and harvested and thoroughly analyzed and with implications made clear. Now, for some of these things that have been extracted using softlet or the microwave assisted process, one will discover that you need to separate them from the solvent or from the material that they were trapped in. And one way of doing that is by the use of the rotary evaporation. The rotary evaporation process is a process whereby the pollutant, which is sensitive to heat, is separated from the solvent that dissolved it or extracted it from the initial surface at a temperature that is way below its boiling or decomposition temperature. If you can extract it way below its decomposition temperature for solids or boiling temperature for liquids, then you are sure that the integrity of the material, the pollutant, is retained and not damaged. That is the essence of using the rotary valve. In this case, I feel that most of us must have seen rotary evaporators, and some of this rotary evaporation, you use vacuum or from vacuum pump to reduce the temperature, the boiling temperature within the system. Some people can also use nitrogen blown down the system to also regulate that. So the other equipment that, the other equipment that we have, which we have not talked about extensively right now, is the gas chromatography or GC. The GC is it makes use of the presence of the material in its gaseous state, and is used for organic pollutants that can be placed in their gaseous states without denaturing them. And we have that the GC separates compounds that are based on the volatility and interaction with the stationary phases. The material that are volatile and they can interact with the stationary phase, the GC will detect them in their volatile nature, volatile state. And that volatile state is what it sees or senses and reads out from the system. Now, the other thing is that it has the detect technique that is coupled to the GC. One of it is the mass spectrometry. When GC is coupled to mass spectrometry, we have a GCMS. And the GCMS has a two-pronged approach. One, the GC detects the presence of the material, that's the pollutant, and the MS detects the quantity of that pollutant. And it's, of course, a gold standard. It identifies and quantifies compounds based on mass to charge ratio, yeah, and provides structural information, because by the time it looks at the mass to charge ratio and the gravitational identity, it matches that with the GC's result of the structural features that it has, because as a volatile nature material, the GC will detect it and identify what it is, and the MS would give us the quantity, tells us about its quantity. It's like a quantity validation, actually. Now, some examples are listed here for us, and we know that it's basically for both target and non-target analysis. Both target and non-target analysis. Now, the other detector is the flame ionization detector, which can also, or is also coupled with the GC. And when it is coupled with the GC, it's known as GCFID. GCFID. It's a universal detector for hydrogen carbons, though less specific than the MS, but it's robust and sensitive. And of course, it's good for specific materials, just like the BTX. The other one is electron capture detector. This is also coupled to the GC, and it gives its highly sensitive nature, particularly in the presence of halogenated compounds. So depending on what you are really targeting and what you are working on, the coupling of the GC matters so much. The coupling of the GC matters so much. And for the GC ECD, it is highly sensitive. It's a highly sensitive material. And one would tailor it down to the halogens or the halogenated compounds, PCBs, OCPs, PCDD, FS. Now, the other one is the photoionization detector, GCPID, which is sensitive for aromatic and unsaturated compounds. So you discover something, that the GCFID and GCPID, they are closely related. So they are GCPID is sensitive to aromatic and unsaturated compounds. Examples also BTEX. So it all depends on what you are targeting, what you want to do, and the pollutant you want to address. That's what determines which coupling you use and which equipment you use for. Now, we also have the high performance liquid chromatography. HPLC. It is used for volatile, thermally labile, or polar organics. Not suitable. I'm trying to get this. Okay, we can go for them. Maybe I'll talk about it later. It's used for it's used for less volatile, thermally labile, or polar organics that are not suitable for GC. Remember, GC is particularly for volatile matter. When the molecular weight of a substance starts getting larger, the rate or the tendency to be volatile reduces. So when you have such materials that are heavy, when their molecular weights are heavy, you discover that GC will no longer work, but the HPLC, high performance liquid chromatography, works better with those materials. And some of these materials are the PAS, aldehyde, and DMPH. Then the detection is by a UV-Vis fluorescence FILD, which is very sensitive for PAS. We also have the LCMS version of detection for heavy materials apart from the HPLC. In fact, the LCMS is basically for liquid samples or samples with heavier molecular weight. So they primarily uses UV-Vis fluorescent for this, the detection. Now, specific challenges with these techniques and equipment are that they are complex. The active formation is there, losses are there, matrix effect is there. What are we looking at when it comes to complexity? Here, because of their capacity and ability, they tend to handle thousands of compounds that are present at trace levels, parts per million, parts per trillion. It depends. So it makes it to be very sensitive to certain pollutants that ordinarily will volatilize when we try to use GCMS, but are stable when you consider the molecular weights. So the complexity of these samples with so many compounds creates a challenge for the use of either the HPLC or the LCMS, as the case may be, or even the GCMS. Now, the sample duration is also a problem because the sample has to be, there is a retention time for it to be able to read the samples very well. Now, that retention time is also a reaction time, particularly when it has to do with ozone, which is very, very reactive, or even the analysis and then thermal degradation. So it becomes a challenge for this set of identifiers. Then the other one is during volatilization, absorption, degradation, during sample storage, there are tendencies for there to be losses, and this contributes to a poor output. Now, the matrix are also meant to undergo a stable integrity, character integrity, as the case may be. But you find out that the duration, if for a matrix that is not very rugged, the duration of exposure may crack up the matrix. And when once that is done, it gives a contamination to the data that will be extracted from the sampling. That's the matrix effects now, interference from co-extracted compounds during analysis. That's another possibility. And these are some of the challenges and struggles with this. Now, quality assurance, quality control, we have QA, QC. How do we ensure that this material is this analysis is well done? How do we ensure out error? Now, why is it essential? Why is it important? It's important because we need to ensure data accuracy, precision, representativeness, comparability, and defensibility, like I've mentioned before. So quality assurance in the essence, becomes an integral part of methodology, because if you don't include it from the onset, you discover that down the line, you will start having problems. You may not even be able to conclude a particular analysis if you are not very sure of the protocol. So it's very important that we carry out quality assurance. It's essential. And the key elements are, one, you must have the standard operating procedures, the SOPs. It has to be detailed, it has to be documented, and the method has to be a step-by-step approach. Now, we also need to have what we call field blanks. They ought to be sealed, not opened, and they are supposed to detect contamination during handling and transportation, so that we are sure that by the time we get to the point of access, that it has not been compromised. Then the other one is the lab blanks. Lab blanks are reagents. They ought to be, they are used to analyze the clean media and solvents, and for us to detect any contamination as the case may be. Some of the blanks are for standardization, some of the blanks are for the analysis itself. Then we ought to have field duplicates, where we collect 2-3 samples side by side at the same time. That's triplicates of samples. And then we assess the sampling precision. This ensures that we have reproducibility assured, accuracy intact, and precision heightened. Then we have a situation where we may need to carry out what is called spiking. Spiking, in essence, is a situation whereby you add a known concentration of a pollutant prepared by you or in the lab in a particular place, and you introduce it into that environment, but knowing its conditions, its parameters, its specifics. You must know this, and what you use to make a comparison of your collected crude or sample. You add a known amount of the target analyte to sample or media, then you assess recovery to get accuracy, of entire method or just analysis. Other things we need to do is the certified reference materials. These are samples with known certified concentrations. They are used to verify accuracy of analytical method. That is why you need them. You know, it's not like you have a standard, you have a sample. Okay, the sample reference material is saying the value is 5. When you bring in your own and it's getting to 5, you know that you are close to the correct thing. So they are used to verify accuracy of analytical method. And they have the calibration standards, which are done by preparing fresh daily concentrations of certified stocks. Now, if you have these multi point calibration curves, which gives you a linearity, you be rest assured that whatever you are analyzing is within the standard of the method, that the method being used, the standard being deployed are within what you have and not outside what you have. That way you are sure that you are accurate and the result is valid. Now, we also have to consider the detection limits. What are the detection limits? For example, you are running a UV analysis. You should be able to say, okay, from a 200 nm to a 400 or 500 or 600 nm, or even to 800, as the case may be. That is the limit I want. Where is your material supposed to be detected? So you don't go too far away from the limit, detection limit. So it doesn't give you a bogus range that you start struggling without real consideration. Now, the other one is the chain of custody. This is documented record of sample handling from collection to analysis. So you give account of every step that you have taken from the point where you collected your samples to the point where you introduce them to the machines for analysis, or you carry out the analysis yourself. That way you ensure integrity. You ensure that, oh, this analysis was done without any undue distortion in information and data handling. So that is where you have the chain of custody documentation. Now we have the instrument maintenance and calibration. Of course, these are simply regular checks and calibration of pumps, flow meters, analytical instruments. However, I must be realistic with you. These days and time, with what is obtained in our different laboratories, we don't have good instrument maintenance and calibration practice. For example, how many laboratories, within the university system, practices this every morning? Equipment must be on for at least 1 hour, calibrated, ready for use, whether there is analysis to be done or not. But for the sake of the accuracy, for the sake of the shelf life of the equipment, for the sake of the fact that it can be called into use at any time, you discover that oftentimes it's only when some of them, only when there is a sample to be analyzed, they start operating the machine. It's not correct. So I think based on that one should be encouraged to remind those that are responsible to please always have these machines powered, always have these machines calibrated, always have these machines working in good order before embarking on sample analysis. Now, the other one is data validation, which is the systematic review of all the QA, CQ data before final reporting. You have to make sure that what you are reporting is the correct, accurate thing. You have to make sure that what you are reporting, for example, you don't approximate your decimals from the first stage of input. It usually comes, if there is need for that, it usually comes at the tail end of input. These are some of the things that generate controversies and then requires revalidation. For us to, we're almost eating up our time for this session of the class. For us to look at these things again, let's summarize this and look at accurate analysis of air pollutants. It's complex but essential for understanding and managing air quality. I hope that is correct. Then we have the careful selection of sampling strategy using either the active or the passive or both of them, as well as the media. And this we have seen to be very critical for representativeness. We also looked at a wide array of sophisticated analytical techniques that have been being deployed now and in the future. We saw the ICP, MS, the IC, the GCMS, the LCMS, the HPLC, as the case may be, and say that they are employed and tailored to the pollutant class. We also looked at inorganics, where we rely heavily on spectroscopic and or electrochemical methods, UVF, CL, DIR, IC, ICPMS. There are lots more. It's not it's not limited to what we have here, but this is just to open your mind to what really is going on. There are many more, and people are working to adapt and evolve, particularly in this present time of AI and the machine learning. Then we also looked at the organics, where we encountered the dominance of chromatographic separation techniques that are coupled with the sensitive detectors. For example, the GCMS or HPLCMS or FLD. Now, we also looked at the rigorous Q. These procedures are non-negotiable, and they are also looked at the challenges that are left for us to handle, but advancements in real-time monitoring, as well as the non-target screening, as well as the sensor technology, what it offers, and the exciting future it opens up to us. And looking at that, you will see that this field underpins the environmental process. Our next class will be looking at analysis of water samples for inorganic and organic pollutants in environmental monitoring. However, at this point, I want to call up for responses, concerns. We just have 10 minutes to go, and we'll wrap up this class while we wait for our next class to look at other things. Thank you very much. Yeah, are there questions? Are there concerns? Yeah, Kanye, thank you. Jibril, are there questions from you? Are there concerns? Thank you, Godwin. Thank you. Yeah, Wilson, thank you very much. Thank you. Sebastian, thank you. Honorable, thank you very much. Yeah, Vashima, I can see you. Edel, Andy. Oh, Osia. Oh, good. I can see your hands. Yeah. Jessica, you didn't want to ask questions. Idu Vivian, how are you? Thank you. Emmanuel. Yeah. Thank you, Tiza. Any questions? You can unmute yourself and express it. Joseph, yeah. Debbie, Dorcas, yeah. Terila. Yande, thank you very much. Winifred. Mark. Kwasanga, Asha, Joshua, how are you? Thank you. Seth, thank you. Brown, how are you? Veshima. Dogara, how are you? Oka, how are you? Tedius. Godwin, how are you? Yeah, okay. How are you doing? Urban, Comfort, how are you? Thank you very much. I assume there are no questions. Do I assume there are no questions? I want your questions.
Okay.
Good morning, sir. Good morning, sir. Can I talk, sir? If you can hear me.
Go ahead. Go ahead.
All right. Thank you very much for the lectures. This is Naniv speaking.
Yes.
Your lectures have been very smooth, well detailed and explained. Thank you very much. I appreciate
You're
it.
welcome. You're welcome. Thank you for that.
You said you would drop the slides on our WhatsApp platform later.
Yes, I will.
Okay, and this lecture has been recorded. I don't know if it would be possible for you to do the for us alongside the slides.
If it's supposed to do what?
For you to drop the recordings for us alongside the slides.
Oh,
as you're dropping this.
Yeah, I will tell ICT if they have that. If they have that in their power to do so. It's not within my powers.
Okay, please help us reach.
I'll tell them that this is your request. If it will be done, it will be nice. Okay, fine.
Morning, sir. This is because along the line we'll be having network glitches, so some of us might miss along the line. It will be very important.
It's okay, no problem. I'll tell them that this is part of your. You can also drop it on the platform too, because they are all there. Both the HOD, the ICT, and everybody. They are all there. We're all there. Dr. Oko, you are around. Say hello to us now.
Good morning, sir.
Good morning, Adoga. Terry, how are you?
Fine, sir. Thank you for your detailed presentation, sir.
You're welcome, sir.
My question today.
Hello.
I think,
Doctor, yes, I can hear you. Doctor, welcome, sir.
Yes, good morning, class, and very thank you for, Dr. Fekwu, for the elaborate discussions. I actually came late, but I think it's very interesting.
Thank you, sir.
And to the participants, I enjoy you to read deeply into this discussion. He has done a wonderful job here. He cannot have more details than what you are seeing now. So please take out time to through all that he has given you. Let me also apologize for my inability to be present yesterday. I happened to be head of department and I was involved in external examination. Yes. And today I came in late the lecture, but I think I'll be with you attending the class.
All right, thank you, sir. We appreciate your presence, sir.
Hello.
Hello.
Hi.
Hello, yeah.
Good morning, sir.
Good morning. Can we have Uche? Uche.
Oh, please unmute yourself, and Mr. Uche, unmute yourself. Mr. Uche, unmute yourself. You wanted to ask a question.
So, Zango, if he's not coming up, call another person.
I have a question, sir.
Okay.
Can I go ahead?
Yeah, Terry.
Okay. So most of your discussion this morning focused on sampling and laboratory analysis. All the analysis techniques and detection mostly has to do with sampling and laboratory analysis. My question is that are they same? Most of those detective materials and items, are they same with sensors instruments where samplings are not needed, are not required to be taken to laboratory? That is one. Then two, is there already a readily established environmental lab in Uniagri where we can have important experience, so that we can have some detailed discussion?
Okay. 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 Let us all mute and let me respond. Can I respond now? Can I respond?
Yes, sir. You can respond, sir.
Okay. Your first question. Your first question is about our lecture this morning centered on techniques and analysis. Yes. Remember, we started from the general introduction and we are zeroing in on the monitoring procedure. And what we did now is to pick them from air, water, and soil. So this morning, if you closely analyze what we did, you will discover that the sampling techniques, the material preparation, procedures, and everything, even the equipment, are all for air quality assessment. So we are taking them in bits so that you will be carried along in calculated order in order to avoid confusion. And like I flashed the next slide, which is going to center on water monitoring. We will discuss that when we come back for our next section. So yes, it is centered on this. Then the other one is, are they also coupled to sensor uses? Yes, the answer is yes. If you go back to what we did yesterday, I said that some of these sensors receive their information based on real-time data of what is happening. You can have a sensor that is coupled to a portable GCMS or a portable UV detector or a portable FTIR, as the case may be. It depends on what you are looking at. Yeah, there is that tendency, there is that capability, there is that option of coupling these to biosensors. And remember, I also mentioned that even these days and times of AI and ML, that these things are meant to interface with each other to give us real-time online situation. If you also remember that I said that at one time, when you want to take analysis of a particular location, you can also use a GIS mapping system to get that done. So yes, they are all linked together and depends on the level of advancement. Yes, in UNAGRIC, I do have a laboratory, environmental sustainability department, setting up a laboratory. If they have not finished, I think they have at the center department. And aside that, as an addendum, there are equipment here and there within the school where you can carry out some of this analysis. Also recall that I mentioned the presence of an air analyzer in the laboratory here, that if any of you can come to school, we would expose you to those things. We have the UVs here, we have the analyzers, we have the ENS, we have some of these photometric analysis. We even have what you call them, this flame photometry. They are all here. It depends on what you are working on, and these projects are designed to suit what we have on ground. But where what you want to do is not here, we also have collaborations outside the university where these things can be done with, ease. So when it comes to equipment, when it comes to handling, analysis, and all that, don't be scared. UNAGRIC, IPES, they are equipped well enough to handle those issues. Thank you very much.
Good morning, sir.
Yeah, good morning.
Please, I have some questions here.
Go ahead, Vera.
Okay, sir. Firstly, I would like to ask, how do we ensure that an air sample is truly a representative of an area, especially when pollution levels change with time and then weather conditions? That's the first question. And then the second question is, on sampling strategy, how do we decide the best sampling frequency and duration? For instance, when to use grab sampling, integrated or continuous sampling? I don't know, how do we decide the best sampling frequency? And then the third question, since passive sampling has lower sensitivity and is affected by environmental factors like the wind and the humidity, in what situation is it still preferred over active sampling, sir?
Okay, thank you. Let me start from the last one immediately. The passive sampling is very effective for preliminary studies where you need to gather preliminary information about a particular location or about a particular incident before going into in-depth study of that situation. For example, let's say there was, this air storm that happened somewhere around us. We may decide to carry out preliminary study and say, okay, let us carry out passive analysis and see what is even happening. Or is there a spewing of lead metals in the atmosphere? Is there, you understand? So when we have that as a preliminary study, we then go into active analysis of the area, the air quality. That way, we would build the case to a conclusive end. Now, I hope that serves for the third question. The second question was about integrity. Now, when you have a situation, for example, if you are studying a particular phenomena, for example, the level of climatic change vis-a-vis air pollution or air contamination or air quality. Now that we are not having very good harmattan, dry season, what is the effect on the environment? What is the effect on the air quality? You have a duration. Remember, we are looking at duration, we are looking at time, and we are looking at the strategy. Depending on what you are studying, you may decide to have an exploration that spans over a period of 3 months, 6 months, or a year. that also confers validity to whatever result or data you are going to collect. I don't know, that should answer the first and the second question because they are interlinked. Does that satisfy your curiosity? Hello, Vera. Are you there? Hello, Vera, are you there? Okay, I can see your sign. That's good. Thank you. So any other question? Hello? Hello? All right.
Hello, Ose. I guess Ose and Abdul Malik have their hands have been up. Ose and Abdul Malik, you can unmute and ask questions.
Okay, let's have the questions.
Hello? Okay, it seems they are not. Okay, Ose is on now. Ose,
yes,
over to you.
Good day, sir.
Thank you.
My concern is on your second slide where you talked about regulatory drivers.
Okay.
I was expecting to see environment, health, and safety guidelines of the World Bank among the regulatory drivers that you mentioned, but I didn't see it. Moreover, owing to the fact that this is a bank-funded project.
Yeah. But there is a WHO guidelines there. If you look at that regulatory drivers.
Yes, I've seen it. I've seen that one.
After EU air quality directives, there is WHO guidelines, which is an all-encompassing thing that has to do with World Bank. You can still have, there are, amongst these ones, these are just like representatives, you understand? Within this range, there are other ones that are found that we can use. These are just examples of it, but we have WHO there, which is about the World Health Organization guidelines. Are you with me? Hello? Hello? Ose? Ose? Ose?
Okay, if he's off, Abdul Malik.
Yeah, I wanted to find out if he's satisfied with the response.
Okay. Also, are you satisfied with the response of the lecturer? Maybe his network have kicked him out.
I think so, yeah. So the next person, Abdul Malik. Abdul Malik.
Are there more questions? I don't think Abdul Malik is with us.
Okay. So if there are no more questions, I think we can end the session for now.
And I mean,
hello. All right. I think we can end the session now. It is 10 minutes after 11. Okay, Abdul Malik is saying that you should allow his.
Okay, Abdul Malik.
Yeah.
Abdul Malik, I've asked you to unmute, so you can unmute yourself. Yes.
Good morning, sir. Thank you very much, sir.
Good morning. Yes.
Hello.
Abdul Malik, we are listening.
Yes, sir. Thank you. Yes, thanks for the wonderful
we are listening, sir.
lecture. In fact, well detailed. Sir, I have two concerns here. The first is regarding one of the one of the requests raised by one of our colleagues here regarding if the
Malik, can you please be more audible?
Okay, I'm talking about one of the requests one of us made about if the record of the lecture can be sent to the group so that we can have access, because when during the lecture, most of us are having network glitches. So I want you to please help us forward the complaint and if it will be resolved and sent to us. Then the second is regarding, sir, hello?
Go ahead, I'm with you. Go ahead. Go ahead.
And the second one is regarding, the second question is regarding or is let me just say in form of a request. I don't know, this course is, to me, is somehow practical oriented, and I think it has to do with more looking at my background of chemistry. So it has to do with more experience, practical involvement. I don't know if the school allows, while we are going to be available for the 2 weeks for the assessment and the revision, if the school will allow us to have a physical contact with you so that we can at least have access to some of these materials, like the instruments that it's required, because most of us, I think, most of us are coming from the end of switching from what we do before into this present course. So I don't know if it will be allowed by the school that when we are in the school for the 2 weeks involvement before the exam, at least we should have access to most of these materials so that at least we can have better understanding of what we've been learning visually. Thank you.
Okay, thank you, Abdulmalik. My response will be for the two questions because they are aligned. I will suggest your class or many of you that are interested in that to write to the HOD. He is the only one. It is outside my jurisdiction. He's the only one that can respond to your concerns when it comes to these access to practical sessions. But I know that 1 week before exam, we usually have review sessions where it's an in-person thing. That time, that is when you will see me and I will see you, we talk and we discuss concerns. That one is already there. But for the practical sessions, I don't know. It's only the HOD that would authorize or permit that. So I suggest you put those things on the platform and tag him. And he is a very, very understanding and responsive person. So he is the only one actually who can do that. Thank you.
All right, sir. Thank you very much, sir.
You're welcome. In the absence of any other questions, I want to end the class. This is 11:14. And for us to have another, you're supposed to have another class or rest or something. So wishing you a wonderful day and looking forward to meeting you by 1 p.m. Thank you.
Thank you, sir.
You're welcome.
We really enjoy your lecture, sir.
Thank you, sir.
Thank you. Thank you very much. Thank you very much.
Looking forward to see you tomorrow.
Thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
See you later.
Thank you, sir. Thank you, sir. We are actually grateful for the lecture.
Well done, and thank you.
Thank you, sir.
Only 50.